Welcome to today's paper reading. Today's paper is titled, MemLong, Memory-Augmented Retrieval for Long Text Modeling. This paper was published on the AR14 preprint by Weijie and colleagues from Juntao University and Harbin Institute of Technology, Shenzhen. The abstract highlights the significant challenges faced by large language models, LLMs, in handling long contexts, primarily due to the quadratic time and space complexity of attention mechanisms and the increasing memory consumption. To address these issues, this work introduces MemLong, a method that enhances long context language modeling by utilizing an external retriever for historical information retrieval. MemLong integrates a non-differentiable ret-mem module with a partially trainable decoder-only language model and introduces a fine-grained, controllable retrieval attention mechanism. Evaluations on multiple benchmarks show that MemLong consistently outperforms other state-of-the-art LLMs. Notably, MemLong can extend the context length to up to 80K tokens on a single 3090 GPU. Large language models, LLMs, face significant challenges due to the quadratic time and space complexity of vanilla attention mechanisms, which limits their ability to handle long sequence tasks. To address this, MemLong is proposed as an efficient and lightweight method to extend the context window of LLMs. MemLong stores past contexts and knowledge in a non-trainable memory bank and retrieves chunk-level key-value pairs for input into the model. This approach ensures distributional consistency, training efficiency, and the ability to extend the context window up to 80K tokens on a single GPU. Figure 1 illustrates the differences between retrieval-augmented generation, RAG, and the memory retrieval flow of MemLong. In Part A, RAG shows a decline in generation performance when the retrieved information exceeds the model's processing capacity. Conversely, Part B demonstrates MemLong's approach, which employs an external retriever to gather historical information and feed it into the model as key-value pairs, enhancing context length handling up to 80K tokens on a single GPU. In this section, we discuss the fundamental approach of language models, which involves predicting the likelihood of a sequence of tokens. Unlike traditional models, we incorporate external retrieval to enhance next token predictions by fusing additional information at the upper layers of the model. Specifically, we partition the sequence into non-overlapping chunks and perform causal language modeling on these chunks. The ret-mem module, as illustrated in Figure 2, consists of a retriever and a memory component, with defined operations and dimensions. The memory module includes KV pairs and representation embeddings, with retrieval based on chunk embeddings rather than KV pairs. MemLong, our proposed model, uses a pre-trained dense embedded to encode chunks into one-dimensional representation vectors, ensuring minimum memory usage despite large memory sizes. Figure 2 provides an overview of the MemLong framework. In the lower layers, the model performs causal language modeling on the entire chunk CI. After processing, CI is cached in both embedding and key-value pair forms. The upper layers of the model are then fine-tuned to harmonize retrieval preferences and integrate the retrieved content effectively. The retrieval process in MemLong involves prefetching information before model input. This is achieved by creating a representation embedding RQ for each query block, which is then used to compute cosine similarity against stored embeddings in Memory-M to obtain the top K indices. The memory process ensures that KV pairs and their corresponding representation embeddings are accurately stored, avoiding redundancy. Dynamic memory update uses a counter mechanism to record retrieval frequency, allowing for selective pruning based on both recency and relevance, thereby maintaining a high-quality dataset. Figure 3 illustrates the retrieval causal attention mechanism. It shows how local causal attention is applied to the most recent context, ensuring that the model focuses on the immediate environment. Additionally, the figure highlights the use of chunk-level key-value pairs obtained through a retrieval method, which allows for bidirectional attention. This approach leverages the historical nature of the data to enable attention across different time steps without causing information leakage. The combination of these techniques enhances the model's ability to process and understand long-term dependencies in the data. In this section, we discuss the experiments conducted to evaluate the performance of our model on long context tasks. These tasks include long-context language modeling, retrieval-augmented language modeling, and scalable in-context learning. For the implementation, we used the OpenLLM 3B model as our backbone, employing the LoRa technique due to hardware constraints. The training was performed on 0.5 billion tokens. We evaluated our model's performance using perplexity metrics on several benchmark datasets, comparing it with baseline models to demonstrate its efficiency and effectiveness. Our model showed significant improvements in perplexity across various datasets, highlighting its ability to handle long-context tasks with minimal memory overhead. Table 1 presents the sliding window perplexity results for various context window extension models across datasets including PG19, ProofPile, Book Corpus, and Wikitext 103. The experiments were conducted on a single 3090 24GB GPU. Models are evaluated both with and without memory, and specific scenarios with 4K and 32K memory are also considered. The table highlights the performance differences and memory constraints faced by each model, with some models experiencing out-of-memory (OM) errors on single GPUs but performing better on dual GPUs. Table 2 presents the accuracy results of 4-shot and 20-shot in-context learning (ICL) on 5 natural language understanding (NLU) tasks: SST2, MR, SUBJ, SST5, and MPQA. The comparison is made between MemLong, the vanilla model OpenLLM, and the memory-augmented model LongLLM. MemLong consistently demonstrates competitive performance across various experimental settings, outperforming both OpenLLM and LongLLM. Notably, MemLong achieves this with significantly fewer training parameters, 200M versus 0.3B, and less fine-tuning data volume, 0.5B versus 5B, highlighting its efficiency and superior ability to synthesize and utilize knowledge effectively. In this ablation study, the focus is on understanding the effects of varying retrieval layers and memory length on model performance. The study reveals that the retrieval layers significantly impact the model's performance and the ability to resolve distribution shift problems, as highlighted by the comparison with MEMTRM. Specifically, the brown line in Figure 4 shows that a method similar to MEMTRM's fine-tuning performs worse than other methods. Additionally, the study examines how memory length affects model efficiency. Figure 5 illustrates that while increasing memory size generally improves performance, there is a critical threshold at a memory size of 65,536, beyond which the model's capabilities see a substantial leap. Lastly, the study investigates the optimal number of retrieval layers needed to introduce extra memory information. As shown in Figure 4 and Table 3, the model performs best when the number of retrieval layers is set to 13, 17, 21, 25, suggesting that introducing retrieval information into all upper layers can decrease the model's attention to local context, but selecting layers at appropriate intervals can enhance the model's capabilities. Figure 4 illustrates the perplexity, PPL, degree during the training phase, with PPL as the indicator on the y-axis. The primary focus is on the effects of training parameters and retrieval layers on the model's performance. Specific parameter settings for each line are detailed in Appendix A. Table 3 illustrates how different retrieval layers impact the performance of MemLong. The table shows that MemLong's performance is influenced by the type of retrieval layer used. Notably, MemLong evaluated without memory is marked with an asterisk. The memory size for all methods using memory is standardized at 32768. The table also defines the retrieval layers: RA for retrieval across all upper layers, TA for training all parameters without freezing, RP for retrieval across fewer upper layers, and RPL for retrieval across much fewer upper layers. Figure 5 illustrates the performance of the same model across various memory sizes, showing a clear correlation between memory capacity and model efficiency. The trend indicates that incremental increases in memory size yield gradual enhancements in performance. Notably, a critical threshold is identified at a memory size of 65,536, beyond which the model's capabilities undergo a substantial leap. This suggests that while expanding memory offers substantial benefits, there is a practical ceiling to its effectiveness, likely influenced by the nuances of the data's distribution. In the related work, two main areas are explored: length extension and context window extension. Length extension studies focus on the rope encoding, aiming to scale unseen positional encodings to generalize during inference. This allows models to extrapolate beyond training lengths. Context window extension, on the other hand, deals with extending the input length that language models can handle at once. This is challenging due to the quadratic time and space complexity of attention computation. Sparse attention techniques have made progress, but our focus is on improving long-range language modeling through retrieval-enhanced methods. Retrieval-augmented language modeling has seen significant effort, with approaches using external retrievers and non-parametric information fusion. However, we concentrate on integrating retrieval concepts directly into the model, enhancing it with a frozen retriever to avoid distribution shifts and architectural changes. In this study, MemLong has significantly enhanced the ability of language models to process long texts by using an external retriever. It successfully expanded the model's context window from 2,000 to 80,000 tokens, demonstrating a 10.4 percentage point improvement in performance. However, the work is primarily focused on the OpenLLM-3B model, and there are limitations such as the instability of single-layer KV pairs and the use of a fixed flag embeddings retriever. Future research should explore these areas further. Additionally, while the work is committed to ethical standards, it acknowledges the potential bias in pre-trained models and hopes for future work to address this issue. Thank you for watching.